Causal structure. In mathematical physics, the causal structure of a Lorentzian manifold describes the causal relationships between points in the manifold. Introduction. In modern physics, especially general relativity, spacetime is represented by a Lorentzian manifold. The causal relations between points in the manifold are interpreted as describing which events in spacetime can influence which other events. The causal structure of an arbitrary, possibly curved Lorentzian manifold is made more complicated by the presence of curvature. Discussions of the causal structure for such manifolds must be phrased in terms of smooth curves joining pairs of points. Conditions and the tangent vectors of the curves then define the causal relationships. Tangent vectors. Fm G is a Lorentzian manifold for metric GR manifold, and then the non-zero tangent vectors at each point in the manifold can be classified into three disjoint types. A tangent vector X is time-like if Gx x0 null, or like if Gx x equals 0, space-like if Gx x0. Here we use the --+++ metric signature. We say that a tangent vector is non-spacelike if it is null or timelike. The canonical Lorentzian manifold is Minkowski spacetime, where m equals latitude 1,1,d4 and g is the flat Minkowski metric. The names for the tangent vectors come from the physics of this model. The causal relationships between points in Minkowski spacetime take a particularly simple form because the tangent space is also latitude 1,1,d4, and hence the tangent vectors may be identified with points in the space. The four-dimensional vector x equals t, r is classified according to the sign of gx, x equals minus c2t2 plus r2, where r latitude 1,1,d3 is the Cartesian coordinate in three-dimensional space, c is the constant representing the universal speed limit, and t is time. The classification of any vector in space will be the same in all frames of reference that are related by a Lorentz transformation, but not by a general Poincare transformation, because the origin may then be displaced because of the invariance of the metric. Time orientability. At each point in M, the time-like tangent vectors in the point's tangent space can be divided into two classes. To do this, we first define an equivalence relation on pairs of time-like tangent vectors. If x and y are two time-like tangent vectors at a point, we say that x and y are equivalent written xy if gx, y0. There are then two equivalence classes which between them contain all time-like tangent vectors at the point. We can arbitrarily call one of these equivalence classes future-directed and call the other past-directed. Physically, this designation of the two classes of future and past-directed time-like vectors corresponds to a choice of an arrow of time at the point. The future and past-directed designations can be extended to null vectors at a point by continuity. A Lorentzian manifold is time-orientable if a continuous designation of future-directed and past-directed for non-spacelike vectors can be made over the entire manifold. Curves. A path in M is a continuous map mu, sigma right R M, where sigma is a non-degenerate interval i.e., a connected set containing more than one point in latitude 1,1,d. A smooth path has mu differentiable an appropriate number of times, typically c infinity, and a regular path has non-vanishing derivative. A curve in M is the image of a path, or, more properly, an equivalence class of path images related by reparametrization, that is, homeomorphisms or diffeomorphisms of sigma. When M is time-orientable, the curve is oriented if the parameter change is required to be monotonic. Smooth regular curves or paths in M can be classified depending on their tangent vectors. Such a curve is chronological or timelike if the tangent vector is timelike at all points in the curve, also called a world line. Null if the tangent vector is null at all points in the curve. Spacelike if the tangent vector is spacelike at all points in the curve. Causal or non-spacelike if the tangent vector is timelike or null at all points in the curve. The requirements of regularity and non-degeneracy of sigma ensure that closed causal curves such as those consisting of a single point are not automatically admitted by all spacetimes. If the manifold is time-orientable, then the non-spacelike curves can further be classified depending on their orientation with respect to time. A chronological, null or causal curve in M is future-directed if, for every point in the curve, the tangent vector is future-directed. Past-directed if, for every point in the curve, the tangent vector is past-directed. These definitions only apply to causal, chronological, or null curves because only timelike or null tangent vectors can be assigned an orientation with respect to time. A closed timelike curve is a closed curve which is everywhere future-directed timelike or everywhere past-directed timelike. A closed null curve is a closed curve which is everywhere future-directed null or everywhere past-directed null. The holonomy of the ratio of the rate of change of the affine parameter around a closed null geodesic is the redshift vector. Causal relations. There are several causal relations between points x and y in the manifold, and x chronologically precedes y, often denoted xy if there exists a future-directed chronological timelike curve from x to x strictly causally precedes y, often denoted xy if there exists a future-directed causal non-spacelike curve from x to y. X causally precedes y, often denoted xy or x less or equal to y if x strictly causally precedes y or x equals y. X horismo is y, often denoted x right arrow y or xy if x equals y, or there exists a future directed null curve from x to y, or equivalently xy and $x $LLY. These relations satisfy the following properties. Xy implies xy. This follows trivially from the definition xy. YZ implies xe xy. YZ implies xe are transitive. Right arrow is not transitive. Right arrow are reflexive. For a point x in the manifold, then we define the chronological future of x, denoted I plus x, as the set of all points y and n such that x chronologically precedes y. I plus x equals ymxy, the chronological past of x, denoted I minus x, as the set of all points y and m such that y chronologically precedes x. I minus x equals ymyx. We similarly define the causal future, also called the absolute future of x, denoted j plus x, as the set of all points y and m such that x causally precedes y. J plus x equals ymxy, the causal past, also called the absolute past of x, denoted j minus x, as the set of all points y and m such that y causally precedes x. J minus x equals ymyx, the future null cone of x, as the set of all points y and m such that x right arrow y, the past null cone of x, is the set of all points y and m such that y right arrow x, the light cone of x, is the future and past null cones of x together. Elsewhere is points not in the light cone, causal future, or causal past. Points contained in I plus x, for example, can be reached from x by a future directed time-light curve. The point x can be reached, for example, from points contained in j minus x by a future directed non-space light curve. In Minkowski spacetime, the set I plus x is the interior of the future light cone at x. The set j plus x is the full future light cone at x, including the cone itself. These sets I plus x, I minus x, j plus x, j minus x defined for all x and m are collectively called the causal structure of M. For Seth, a subset of M, we define I plus or minus equals xc plus or minus x. J plus or minus equals x s j plus or minus x. For S, T2 subsets of M, we define the chronological future of South relative to T. I is the chronological future of South considered as a submanifold of T. Note that this is quite a different concept from I plus T, which gives the set of points in T which can be reached by future directed time-light curves starting from South. In the first case, the curves must lie in T. In the second case, they do not. See Hawking and Ellis. The causal future of South relative to T, J, is the causal future of South considered as a submanifold of T. Note that this is quite a different concept from J plus T, which gives the set of points in T which can be reached by future-directed causal curves starting from South. In the first case, the curves must lie in T. In the second case, they do not. See Hawking and Ellis. A future set is a set closed under chronological future. A past set is a set closed under chronological past. An indecomposable past set IP is a past set which isn't the union of two different open past proper subsets. An IP which does not coincide with the past of any point in M is called a terminal indecomposable past set TIP. A proper indecomposable past set PIP is an IP which isn't a TIP. I minus x is a proper indecomposable past set PIP. The future Cauchy development of S, D plus S, is a set of all points x for which every past-directed inextendable causal curve through x intersects South at least once. Similarly for the past Cauchy development. The Cauchy development is the union of the future and past Cauchy developments. Cauchy developments are important for the study of determinism. A subset SM is a triangle if there do not exist Q, are S such that I plus Q, or equivalently, if South is disjoint from I. Some causal diamond a Cauchy surface is a closed triangle set whose Cauchy development is M. The metric is globally hyperbolic if it can be foliated by Cauchy surfaces. The chronology violating set is a set of points through which closed time-light curves pass. The causality violating set is a set of points through which closed causal curves pass. The boundary of the causality violating set is a Cauchy horizon. If the Cauchy horizon is generated by closed null geodesics, then there's a redshift factor associated with each of them. For a causal curve gamma, the causal diamond is j plus gamma j minus gamma. Here we are using the looser definition of curve whereon it is just a set of points. In words, the causal diamond of a particle's world line gamma is the set of all events that lie in both the past of some point in gamma and the future of some point in gamma. Properties. See Penrose 1972, p13. A point x is an I minus. Y if and if y is an I. It's xy minus, xi minus, yxyi, yi. Xi plus equals I plus j equals j plus I minus equals I minus j minus equals j minus. The horismos is generated by null geodesic congruences. Topological properties. I plus or minus x is open for all points x and m. I plus or minus is open for all subsets sm. $I backslash pm equal a backslash pm $, for all subsets sm. $backslash over line s$ is the closure of a subset South. $I\bm /subset/overline J\pm Conformal geometry. Two metrics G and G are conformally related if G equals omega 2 G for some real function omega called the conformal factor. See conformal map. Looking at the definitions of which tangent vectors are time-like, null, and space-like, we see they remain unchanged if we use G or G. As an example, suppose x is a time-like tangent vector with respect to the G metric. This means that G x 0. We then have that x equals omega 2 G x 0, so x is a time-like tangent vector with respect to the 2. It follows from this that the causal structure of a Lorentzian manifold is unaffected by a conformal transformation. A null geodesic remains a null geodesic under a conformal rescaling. Conformal infinity. An infinite metric admits geodesics of infinite length / proper time. However, we can sometimes make a conformal rescaling of the metric with a conformal factor which falls off sufficiently fast to 0 as we approach infinity to get the conformal boundary of the manifold. The topological structure of the conformal boundary depends upon the causal structure. Future-directed time-like geodesics end up on I, the future time-like infinity. Past-directed time-like geodesics end up on I minus the past time-like infinity. Future-directed null geodesics end up on letter 2110, the future null infinity. Past-directed null geodesics end up on letter 2110 minus the past null infinity. Space-like geodesics end up on space-like infinity. For Minkowski space, I plus or minus are points, letter 2110 plus or minus are null sheets, and space-like infinity is codimension 2. For anti-de Sitter space, there is no time-like or null infinity, and space-like infinity has codimension 1. For de Sitter space, the future and past time-like infinity has codimension 1. Gravitational singularity. If a geodesic terminates after a finite affine parameter, and it is not possible to extend the manifold to extend the geodesic, then we have a singularity. For black holes, the future time-like boundary ends on a singularity in some places. For the Big Bang, the past time-like boundary is also a singularity. The absolute event horizon is the past null cone of the future time-like infinity. It is generated by null geodesics which obey the ratio theory optical equation.